panelist, Sri Abhijit Hajra, SR Manager, CESC. I would request him to please kindly present his PPT and let's also give him a big hand. Thank you.
Respected panelists on the dais, all the assembled delegates and officials of the Employee Welfare Forum of WBPDCL. Very good afternoon to all of you. I am representing CESC Limited, and my presentation I would like to share with you some of the practices that we are adopting in order to remain competitive, because today's seminar's topic is competitiveness of Indian thermal power generation and national energy excellence drive. So the presentation would be basically of some practices that we follow at CESC, and some other the balance part would be on some of the international benchmarking, especially with respect to Japan, that we are visited recently. So a brief note about the power group of CESC. We are, as many of you know, we are a 118-year-old company. We have subsidiaries in retail and real estate, and we have supplying power to the city of Calcutta, that everybody knows, with 3 million consumer base right now, and 3 thermal power plants in and around the city, 1125 megawatt capacity, and we also have 40 megawatt operated by our subsidiary in Asansol, AFBC plant, and we have also diversified to wind and solar, but that is not in West Bengal, it is in the states of Rajasthan, Gujarat, MP and Tamil Nadu. So 27 megawatt of solar and 86 megawatt of wind power. As I was telling, we have 3 thermal power stations. The earliest one was Titagarh, set up in 1982. That is 240 megawatts. Next we had Southern Generating Station, set up in 1990, 67.5 into 2. And the latest was Bajbaj, 3 into 250 megawatts. And started in 1996, 97. And the third unit was finally put up in 2009. Basically, 90% of generation currently is from Bajbaj, and as I've said, that due to higher fuel cost, the older plants are being gradually phased out and they contribute considerably less to the system. So the competitiveness has somewhat been lost for these 2 plants, and that is why the generation has been reduced. So this is a brief idea about the import, generation and distribution scenario for Kolkata licensed area for the last financial year. The total units delivered to CESC system, that is the 567 square kilometers, was 10,685 million units, of which the power generating stations contributed 6,400. About 4,000 came from Haldia Energy, and the unit sold was 9,225, and a small amount was exported. So basically what we want to say is that 60% of the power is now coming from Bajbaj, and rest about 40% is from Haldia and the power exchange. We do have to import power from the power exchange sometimes. So basically, in tune with today's topic, that is competitiveness, as I was telling you, I would like to share some of the practices that we do to keep the PF, PLF, etc. of CESC plants at a high level. So basically, these are all listed here. That is VW operation, keeping all parameters under limits, for keeping high availability of plants, regular soot blowing to ensure full loading capacity. It is done in every shift, that is thrice a day, almost all the days. And some of the earlier speakers were telling, a judicious blending of coal. So we have to have some imported coal. We buy coal from BCCL, we buy coal from ECL, and we also buy coal from MCL. So some of them are very high in calorific value, some of them are low. So we resort to blending of coal in order to get the correct value of coal in the boiler, which is around 3,800 to 4,000. That is the design requirement. As the graph beside this shows the Bajbaj basically parameters. So So we are having a very high level of PLF, and in 15-16 it has shown a decrease. That is because of the increased generation from the Haldia plant. Some other best practices that we would like to share with the personnel assembled here is that for the availability factors, we have to keep the outage period down. That is why we have resorted to working in 3 shifts, and our forced outage periods and planned outage periods are one of the shortest. So some of the other things which have helped us in reducing the overall period, the planned outage period, are the use of sky climber for fast scaffolding inside the boiler. We are practicing forced cooling of all the turbines in the CSC system. Earlier, for the plant shutdown to start, it used to take 3 days for the turbine to cool down. So, but we have now we are employing forced cooling on all the turbines in CSC system, and within 24 hours we are able to start work. So this forced cooling, of course, this has been done in collaboration with the OEM, and they have permitted to use forced cooling, that is with air, and this has helped us to reduce the period. Consider this is only 1 day before we can start the job. Earlier it used to be 3 days. So one other factor is we attend the tube leakages which are occurring very fast, and enhancing reliability of boilers. That is, everybody does this. Every 2 years we have a major overhaul, and every alternate year we have a short 3 to 4 days outage for checking of the boiler mainly and cleaning. Other than that, we are practicing daily maintenance planning meetings for carrying out planning every day's work. And one other thing which we have like to mention here is that for the turbine, we have adopted the blade vibration monitoring system because subsequent to a major failure in Tata Power, which had experienced a blade failure with the BHEL made machine, our machine is also of similar type. So we have also installed this blade vibration monitoring system in 250 megawatt third unit of Bajaj, and not in all the units. A few other best practices for improving the energy efficiency. As you can see in the graphic alongside, our auxiliary consumption is steadily declining. From 8.2% to last year we have finished at 7.97. Last year we finished at 8.05, and this year currently it is 7.97, which may go up slightly because the outages are all in the latter half of this year. So how are we able to do this? This continuously decreasing auxiliary percentage. So some techniques, and some techniques are not all our own brainchild. We have adopted significantly by benchmarking visits to other power stations, and by attending similar seminars, national level meets at various fora. And we have incorporated, we have a large number of boiler feed pump. Next, we had in the Bajaj 2 units, we had tubular air heaters. So these tubular air heaters were, quite old. They were almost 18-20 years old, and they have recently started, showing a large amount of leakages. So what we have done is we have carried out retubing in one of the units, and another retubing is due in this year. And to track the auxiliary consumption, we have installed the auxiliary energy monitoring software by Schneider, and that way we are able to keep a daily track on all the auxiliary consumptions of the. We keep a note around the kilowatt per megawatt consumption of all the major auxiliaries. So that has also helped us to keep track of the auxiliaries consumption on a daily basis. So one other major thing which many of you may have already done, the CEPs are generally over-designed in many plants. So what we have done is to reduce one stage of the CEP to give a better power consumption and improve power consumption in the CEP. That is what we call stage blinding of the CEPs. And we are also slowly converting to LED lighting and the reduction in feed control station DP by simple modification of the logic. So the feed control station DP is now only 1.8. So as far as energy efficiency, a bit some more practices that CSC is following. That is, as some of my earlier speakers were also telling about this, we carried out detailed thermography analysis of the boiler insulation. And to our surprise, we found that since insulation is normally a neglected area, but when we carried out this thermographic analysis of the insulation, we found that temperatures almost in the range of 200 to 250 are there in some locations. Basically from front pass to back pass, that vestibule area is very, very high in temperature. So we spent a lot of money in renewing the insulation and also the design change, because in 1995 the APL boilers, they were designed with only 105 millimeter thickness of insulation, whereas the new generation boilers are now the third unit of Bajaj, they have 160 millimeter thickness. So basically there was a reduction in, that time the design is not considered the fully the energy efficiency part of it, and now the high heat loss zones have already been changed to 200 millimeter insulation, the high heat loss zones. So boiler insulation thermography and necessary correction, that is the changing of the design to higher thickness, and we carry out in-house measurement of TG heat rate and boiler efficiency. In fact, my department, we are currently carrying out in-house boiler efficiency and turbine heat rate tests. So these are carried out on a bi-monthly basis and TG heat rate on a monthly basis. And feedback is given to all the stations about their current performance levels. So one other thing that we have practiced is that cleaning of heaters, especially the HP heaters. So heaters were also one area which was neglected by and large, but we have learned from one of our collaborators, that is J Power, and that HP heater cleaning can also give benefits. So we are Indian agency based in South India. They have carried out the HP heater cleaning by water jet only, and in southern generating station they carried out by acid cleaning and low concentration of acid, and that has led to significant gain in the feed inlet temperature by around 3 to 4 degrees increase in feed inlet temperature, which leads to a rise in efficiency. And we have installed PADO by STIAC, that is for effective monitoring of the two boilers at Bajaj generating station. And in-house effort is a decision support system which we have developed in-house for Bajaj's third unit, which is BHEL make. So as I was telling, the best practices means a lot of interaction among stations, interaction among companies, and some of the exchange of ideas which take place in fora like this. So we have practiced like whatever we have learned is through some of our own ideas and some of our ideas which are shared by the peers in the industry. So this is what benchmarking is about. I won't go through the details of all this. So some of examples that CSC has, of benchmarking that we have, our teams have visited these power stations, and this Reliance Energy, Dahanu, some Dadri, Ramakunda, Vindhyachal of NTPC, Trombay, Tata Power, this Jharsuguda, Sterlite, Vedanta, Tamnar of Jindal Power, and the Black and Beach remote monitoring facility, and Tata Power remote monitoring, because we are also going to introduce remote monitoring for the stations. And at the international level, our senior officials have gone to Japan. So Isogo and Takasago of J Power, which I am going to show in the next slides, and also to some plants in the USA. So all the result is reflected here. This is the current year's 2016-17 top 10 performing thermal power plants on the YTD PLF, and in July Bajaj was ranked number 1. So it's a major achievement for us. The earlier months also we were placed within the top 10. Okay, so some details about what we have learned from where. So from Dahanu we have learned about the noise analyzers and VFD drives. From Tata Power, the blade vibration monitoring system, which we have already installed. And from Sterlite, Jharsuguda, the PADO, we have seen that they are using PADO, and we have also implemented. And from Jindal Power Raigad, CFD analysis and isokinetic sampling of PF, clean air and dirty air testing, and which we have started doing in Bajbaj. From Okreshwar of WBPDCL, we have seen the maximum of IBM at work, and we have identified similar application by Reliasoft for reliability centered maintenance. And Dadri, we have learned how they are monitoring the efficiency by in-house all the instruments and the methods. And my department is currently, we are practicing all this. So some other benchmarking examples, like these are international benchmarking, which from Japan we have learned about the small area of power plant. Their most efficient insulation, their housekeeping and centralized vacuum cleaning. From the Takasago power plant of Japan, we have learned about the HP heater cleaning and the turbine overhauling, which they are carried out every 4 years. And we are currently every 6 years. So there is an agency called Navigant Technologies, which provide details about all the international power plants. So we have subscribed to their website, and we are getting the details of international plants which they are giving. And so we are doing the international benchmarking also. So as I was telling you, some of our senior officials, they have visited Japan recently last year, and the J-Power 2 plants they had visited, but there is a lot to learn from what they are currently practicing. So the most surprising part is 1200 megawatt in 30 acres only. 1200 megawatts, 30 acres. This is unimaginable for us. And ultra supercritical, 250 kilograms per square centimeter, 620 degrees centigrade, and thermal efficiency of 42.5. We are now at 35, 36, 37. They are at 42.5. which is equivalent to a heat rate of 2023 kcal per kWh. And pollution levels are best in the world, and this plant is located in a very, very densely populated area. Coal is received by ships. I will show you the picture, that way we will be able to understand better. So ultra supercritical conditions, tower type boilers, dry type, flue gas desulfurization and denoxification, and tandem compound steam turbine. So the boiler is an RC building, basically on 4 RC slabs. That was the first time in Japan they did it. The turbine building has the office and the occupation centers. They have a covered coal silo. Coal is not kept in the open. It is kept in covered silo with circulation of coal and beautiful landscape. Right. So this is the picture. It's not very bright, but the red boundary area, the right hand side of the red boundary area is the plant. Only 30 acres is the area of the plant, and these are the 2 boilers. This is the coal silo. So the coal silo is covered coal silo. There is no open coal stockyard. There is a covered coal silo, and 1 lakh ton in each coal silo. And basically, this is the stack. The coal is coming in through ships. There is a covered conveyor which takes the coal to the coal silo, where the coal is getting circulated. And basically, the boiler on the side, there is a FGD unit, and only the right hand side of the red boundary line is the plant. Very small area, 1200 megawatts, and they are using Australian and Indonesian coal only. So this is a close-up shot of the, this is called Clover type coal silo. They have 4 numbers, and this is for saving the space. And the conveyor belts that carry the coal have air floating type belts, which I will show you. And there is no dust at all. No covered conveyor belt inside a pipe. And there are no idlers, only air pressure is keeping up the conveyor. So covered coal silo. So this is the coal conveyor. It's a covered conveyor. The belt, there are no idlers. It's called airlift type sealed tube conveyor and idlerless. There is no fugitive emission. So they have a FGD unit, and FGD is it's a traveling, it's a desulfurization, it's a dry activated char absorption with sulfuric acid recovery, and flue gas is going up, and activated charcoal bed is coming down, and ultimately the end product is, the byproduct is sulfuric acid. What is most interesting to note is the pollution level. So for denitrification, they have dry catalytic reduction with nitric oxide with ammonia, and that is also there. So both FGD and denoxification is carried out, and this is the output of that FGD and denoxification. The NOx ppm, their government, Japanese government regulation is 200. They are running at 20 and 13, that is NOx. Fantastic levels of NOx. Look at the SOx. Government regulation is 60, they are running at 20 and 10, unimaginable for us. And SPM, government regulation is 50, they are running at 10 and 5. So these are mind-boggling figures, but that is the use of technology by J-Power. We hope to achieve this sometime in the future. So some tips about maintenance days. So contrary to what we practice, we try to finish the 4 stoppage periods in a very short period of time due to lack of enough schedule. So we are scheduled 15 days, so we have to complete the overall within 15 days. The Japanese don't believe in that philosophy. They believe that the work should be done and all the jobs should be completed. So there, basically, the 500 megawatt units, the boiler major overhauling is done in 63 days and turbine minor 43. And anyway, the main thing to be emphasized is that their outage periods are not low. They carry out all the jobs in great detail and their outage periods are high. And one other thing is that every major overhauling of the turbine is carried out in 4 years, because they believe that after 4 years the turbine efficiency degrades and it is better to carry out the overhaul in 4 years. Current CSE practice is 6 years, and we are thinking of moving to 4 years, because the loss in heat rate that occurs in the next 2 years will be more than offset by the increased efficiency. So in this comparative analysis, so boiler major overhauling 43 to 55 days, ours is once in 2 years, theirs is also once in 2 years, but we are now 50 to 30 days. So as I was saying, they go for a higher outage time. And turbine major once in 4 years, as I was telling you. Okay, so as I was telling you, there is a reduction of PG heat rate with time. So the government has made the turbine overhaul mandatory every 4 years to revert back to the design heat rate levels. So this is another graph of the efficiency that they are operating and where we are operating. Of course, this is a bit old, so they have increased, and whereas we have more or less remained at the same level of 34 to 35%, and that is the relative difference is about, I think, 6 to 8% in thermal efficiency. Right. Thank you for your patience, and at the end I would once again thank the organizers of the Engineers Welfare Forum for excellent organization of this seminar, and thanks once again.